Hi, and welcome to the Unit 5 study guide. It's about modules 10 and 11, and module 10, as you can see, is about analyzing and comparing data. So the main ideas here are right here. Our essential question is, how can you solve problems by analyzing and comparing data? And they talk about shapes and centers and spreads, and you can read all that. These are box plots. And box plots, to remind you what box plots are, back from 6th grade, this has a bunch of data. So a box plot will have, right here, this is the median of the data. This is the lower quartile. This is the upper quartile. This is the largest number, and this is the smallest number in the data set. And we're comparing these two. And we can see that overall, Charity B, this is 75% of the data right here. From here to here is the median, which is the middle of the data. And that means that this is the first 25%, this is the first 50%, this is the first 75%. So only 25% of the data is here. 75% of the data is here. It's well below Charity A, where here 75% of the data is from here to here, right? Because that's 50%. And each part of the box, 25, 25, 25, 25%. So when they were talking about this right here, let's bring this down just a little bit. So the shapes, okay, they talk about the shapes and so on. It has a long whisker, blah, blah, blah. The median, okay, they talked about the medians for the centers. And the interquartile range is the upper quartile minus the lower quartile. So they talk about 44 minus 32, right here is 12, and this is 24 minus 14, which is 10. And overall, Charity B was lower, okay, because that's 75% of the data. Now let's get to these dot plots. This was the first section, and here they want the medians of the dot plots. So the medians of the dot plots, you gotta do this. You gotta do let's see, knock this off and that and that and that and that and that. Let me make this bigger. This and this and this. So we can say, obviously I'm finding the middle number. The middle number is like the 6 right here. So the median median is 6 hours. Okay, that's pretty easy. And then we have the average time in minutes the students spend studying and watching. So we need to find the means for each of them. And the means, let's see, we need to get the total. So the total divided by, I think there's 8 numbers here. So the total of 25 plus 30 plus that plus that plus that plus that plus that plus that. And that total, I believe, is 400. And 400 divided by 8, that is 50. So for studying, the mean was 50 minutes. And for watching TV, that average, let's see, there's still 8 numbers here, and we need that total. And the total is 360, and that is equal to 45. So that's 45 minutes. Okay, so now we're going to do something really new. Find the mean absolute deviations, the MADs, for each data set. I'm going to copy this here. And I'm going to bring it out over here so I have some room to work with here. And okay, so the mean absolute deviation. I like to work with white on this. So the mean absolute deviation. first we start with the mean for studying. The mean for studying, I'm going to have to do this in red. The mean for studying, let me erase this stuff here. Oops, that's not good. Oh well. Okay, I know what I'm going to do. Ah, okay, I was able to fix that. So what I'm going to do is I'm going to do this in green. Okay, I have to compare 25, 25 to 50. What is the distance between 25 and 50? It's 25. So I write 25. This is the deviation part of the mean absolute deviation. How far does each number deviate from the mean? Well, that deviates 25. How far does 30 deviate from the mean of 50? Well, that's 20. The difference between those two numbers is 20. And the difference between 35 and 50 is 15. And 45 and 50, well, that deviation or that difference is just 5. And 60 and 50 is that deviation's 10. And 60 again is going to be 10. 70 and 50, that difference is 20. And 75, the deviation or the difference is 25. Now we're going to take, so the mean absolute deviation, we have all those deviations. We're going to add them together. And we're going to divide it by the amount of numbers we have, which is 8. And I believe that when you take that sum, let's see, what is the sum? Ah, yes. The sum is 130 divided by 8, which is 16.25. So this is the mean absolute deviation. And what it means is the average each number deviates from the mean on average 16.25 points away. So it tells you how far spread out your data is away from the mean on average. So we'll now do watching TV. I'll do that in yellow. So TV. And so now we're going to compare 0 to 45. And that difference is 45. And 35 to 45, that is 10. 35 to 45 again, that's 10. And 45 to 45, well, that deviation is 0. 50 to 45, the deviation is 5. That is again 5. And this is, 25. And this deviation is 30. And we take all that and we divide by 8. And I believe that that sum is also 130 divided by 8. So that mean absolute deviation is also 16.25. So the mean absolute deviations for both, so it's 16.25 for both data sets. Find the difference in the means as a multiple of the mean absolute deviation. Okay, well, to do that, okay, I'm gonna take this here, right here, and I'm going to bring it over here and show you what this means, because I always have to slow this down a little bit. Find the difference of the means. So what is the difference of the means? Well, if we remember, the means are 50 and 45. So the difference in the means is 5. So 50 minus 45 is 5. And the difference of the means as a multiple of the mean absolute deviation. So what that means is the difference of the means is 5. So that would be 5 over the mean. You could pick either mean absolute deviation because it's 16.25 for both of them, divided by 16.25. And I got my calculator here. 0.5 divided by 16.25 is 0. It's a big old decimal, so I'm going to say it's about 0.307, which rounded to the nearest hundredth, 0.31. So there it is, 0.31, and there, oops, so that's 0.31. Okay, so there's module 10 for you. And what we have next is module 11. And that one's all about random samples and populations. And so in this, the essential question is, how can you use random samples and populations to solve real world problems? And our key vocabulary that would be good to look up are bias sample, population, random sample, and samples. So just to let you know, bias sample, it means that, well, one group was more heavily biased, or it's overweighted from the other representative groups. Maybe you have more sixth graders than you have seventh graders in the sample. Population is the who's in the sample. Random sample, that's what you're going for. You want it to be random. You want it to be balanced among all the populations. And then your sample is just, well, what's your size? What you'll see here, we'll have some uses of it where there is, and I'll go through this quickly. An engineer in a light bulb factory chooses a random sample of 100 light bulbs from a shipment of 2,500 and finds that 2 of them are defective. How many light bulbs in the shipment are likely to be defective? So we can set up a proportion for this. If 2 random sample so 2 of them out of the 100, so 2 out of 100, well, then how many would be out of the full 2,500? And you would solve that proportion to get 50. So there you go. And then in the second example, well, there are 300 students in a school are about to vote for student body president. There are 2 candidates, Jay and Serena, and each candidate is about the same amount of support. Use a simulation to generate a random sample. There's a lot of stuff here, right? Digits 0 through 9 on index. So they're making a modeling the situation. 0 through 9 on 10 index cards, 1 digit per card. Draw and replace the card 3 times to make a 3-digit number, because there's 300 students in there. That's 3 digits right there. And then so repeat this process until we have a sample of 30 3-digit numbers. So they're going to draw. They're trying to create 30 a sample of 30 3-digit numbers, and each number is going to represent a student in the school. So what they have is they have these, they have 83. I know that's 2 digits, but it could have been 083, 037, 016, 004, and so on. So anyway, here are the students that they got. Each number represents a student in the survey. And notice that 18 of the 30 numbers represent votes for J. So let's see. For example, okay, if you draw 108, 108, repeat this process. So we're going to let the numbers 1 through 150 represent votes for J. So I'll put, well, those numbers are represented right here for J, right? And then Serena, all those votes for Serena ended up being here. So there should be 18 numbers for 18 of the 30 are for J. So if 18 out of the 30, that means that here they've already calculated 60% of the 300 votes, or 180 votes. Based on the sample, J would win because he got 18, and what she must have got 12 then, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. Okay. Now, here is an important, repeating the simulation many times and looking at the pattern across the different samples will produce more reliable results. So this is a small sample. They're saying if we would have sampled more times, we would have got a much more reliable result. Okay, so moving on to that last page. Let's see now. Molly uses the school directory to at random select at random 25 students from her school for a survey on which sports people like to watch on television. She calls the students and asks them, "Do you think basketball is the best sport to watch on television?" Did Molly survey a random sample or a biased sample? Well, it looks like she definitely did a random. She selected them at random, so that would be random. Now, the other question was here. Was the question she asked an unbiased question? Explain your reasoning. I believe it was biased. And it assumes uh, the person uh, watches basketball. Now that's just a sample idea, but I mean, think about the question here. Do you think that basketball is the best sport to watch on television? That's kind of leading towards basketball on that. That's, it would be better if she just asked, "What do you think the best sport to watch is on television?" That's a more unbiased question. Okay, there are 230 licensed dogs in Clarkson. A random sample of 50 of the dogs in Clarkson shows that 8 have ID microchips implanted. How many dogs in Clarkson are likely to have ID microchips? This looks like it'll be a proportion. I'm going to set up that proportion right over here. So I'm going to shrink this a bit. So let's see. 2,300 dogs are licensed. 8 of the 50. Okay, so there we go. 8 out of the 50 are in this random sample are licensed. So that how many out of the 2,300 would be licensed? Now, what I would probably do is I'd probably use that butterfly effect. So 8 times 2,300. Um, let's see. 23 times 8 is 4, 2, 16, 17, 18. So that'd be 184 with two zeros divided by 50. And you can knock these out. So that would be 3, 34, so 6, and then 8. So I think 368 dogs would be it. 368 dogs. There you go. Okay, so let's look at this one. A store receives shipments of MP3 players. Historically, about 25 out of every 500 players are defective. Okay, that's important information right there. I'll highlight that. 25 out of 500, and the rest are working. The store receives a new shipment of 300 players. So that's important information. Oops. Highlighter, please. 300 players. The store has a random sample of 20 players. Okay, how many players in this sample are expected to be defective based on the historical defective rate? Okay, well, let's see. I'm going to make this a little bit smaller so I have some room to work here. So 25 out of historically, 25 out of the 500 players are defective. So let's see. That is 1 out of. Oh, okay. Actually, I don't have to do it that way. I could do it this way. So out of a random sample, so how many out of a random sample of 20? Well, we would take 25 times 20 and divide it by 500. 25 times 20, 4, I believe that's 500. Yeah, that's 500. So 500 over 500 is 1. So x would be, so 1 out of every 20. how many players in this so I would expect one. Uh, okay. So here they're saying that a graphing calculator can be used to generate 20 random numbers to simulate the problem. So let the numbers 1 through 25 represent players that are defective. So defective. Sorry. Yeah. And 21 to 500 would be working. Okay. Based on the sample of 20 players, how many players are expected to be defective out of 300? Um, well, 25 out of 500 equals how many out of 300? That would be 25 times 300 divided by 500. You know what? We can knock these zeros out, and 25 times that's 75 over 5, which is 15. So we should expect about 15. And yeah. And then how does the sample contrast with the historical player rate? What might you infer about the last shipment? Okay, so back to this using a graphing calculator, I generated 20 random numbers where 1 through 25 represent defective and 21 through 500 represent working players. And so 1 through 25 are defective. So here we go. This should be 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 1 through 25. Let's see, I'll put them in a circle in blue. So this is 1, 2, just 2. Okay, so it's 2. 2 out of 20, which is 1/10, which is 10%. So what actually happened here was 10%. And so here we go with this. How does the sample contrast? So how's our sample contrast with the historical? So remember, the was historical was 2 out of 20. I'm sorry, no. Sorry. The historical they gave us up here, it was right here, 25 out of 500. And so maybe I'll write it down here. Historical was 25 out of 500, which is equal to, dividing both by 5, that'd be 5 out of 100, which is 5%. But from my sample over here, it was 2 out of 20, which is 10%. So that is, sample is 10%. So how do they contrast? The sample rate was twice the size of the historical rate. And so there you go. There is the complete study guide for, let's see, Unit 5, I believe, on modules 10 and 11. Lots of data, analyzation, such. And I hope you found it useful. Thanks for watching.